Hello, you are welcome to today's tutorial. In my previous video, we got the opportunity to talk about or discuss antiderivatives as an area. And from there, we were able to solve 2 or 3 examples. And we also came into conclusion that how do we approximate the area if the rate is also a curve or is curvy? If the rate of change is what? Curvy. For instance, like for functions representing other rates such as the production of a factory or the flow of water in a river or a traffic over a bridge or the spread of disease. Now, this is where we realize that we can use another technique called Riemann summation, of which you can also call it approximation with rectangles. So today we are going to discuss an approximation with rectangles, which is Riemann sum. Riemann sum is a method that allows us to determine the area under curved graphs. As you can see over here, this is a curved graph. We can use these rectangles to approximate the area under this curve, which can be given as y equal to f of x, a continuous function over an interval, which is or maybe a and then the b. Riemann summation can be accomplished with the use of summation notation, and therefore we also take a look under that. And aside with the summation notation, you can see the figure over here with an interval of a to b, and it's divided into 4 sub-intervals, 1, 2, 3, 4, and each also having some weights, and then the weight is being calculated by the change in x equal to the b minus a all over n. So when you look at the figure here, we can see that the height of the rectangles shown are f of x1, f of x2, f of x3, and f of x4. So the area of the region under the curve is approximately the sum of the areas of these 4 rectangles, right? So these 4 rectangles, as I said, the area of this region under the curve is approximated by the sum of the areas of these 4 rectangles. So in this case, what can we say about the rectangle? So for an area of a rectangle, we can say that area equals length times breadth. So in this case, the length we replace it by width, and then the breadth we replace it by what? Height. So that's something that I need to take note of it. So now our height becomes our f of x1 and then f of x2 and so on, as we have indicated here. And then the length, which is our width, is also indicated by the change in x, as also indicated over here. So as you can see, which is what? B minus a over n, where the n is the number of sub-intervals. So we can donate this sum with summation notation or sigma notation, which uses a Greek word. So I know you are familiar with this notation, which is, for example, maybe here I equal to 1, and then the subdivision is up to 4. The iteration will be up to 4, and then f of x. So the f of x I, and then the change will be what? X. So this particular one is the area of a one rectangle. So if I equal to 1, we approximate the area of the first rectangle, plus it will be continuous, maybe f of x2 change in x, f of x3 change in x. So we approximate the area of each rectangle here, and then at the end of the day we sum them together to get our total area under the curve, of which we call Riemann summation or Riemann sum, of which we can also pronounce that approximation with rectangles. So basically, let's look at something here. If you want to represent these ones, 2 plus 3 plus 6 plus 8 plus 10 plus 12 and so forth, as summation notation, what you can do is that the consecutive or the consecutive term that we are multiplying is a 2 consecutive, because here the difference is 2, the difference is 2, the difference is 2, the difference is 2, the difference is 2. And therefore, if we are writing that as summation notation, you can write it as this sigma I give us 1 up to how many figures we have right now here? 1, 2, 3, 4, 5, 6, right? So up to 6, and then the difference is 2, and then we can bring I. So the I is equal to 1, 2, 3, 4, 5, 6. So at I equal to 1, we have the 2 here. At I equal to 2, we have the 4 here. At I equal to 3, we have the 6 here, and so forth. So that is it. You can also write a summation notation for various terms as well, or you can express, let's do this example, express this summation notation I equal to 1 and then 4, and here will be 3I. So you can pause the video and solve it. Now, what we can do is that for this summation of 4, I equal to 1, 3I, is the power I, is equal to 3 power 1 plus 3 power 2 plus 3 power 3 plus 3 power 4. And at the end, you are going to sum. Power 1 is 3, power 2 is what? 9, and so forth, and so basically at the end of the day you are going to get 120. So this is how things has been. So you can also look at this. You can also express this 30, I equal to 1 each of x, I change in x, without using summation notation. So with this, what you can do is that you can also do something like this sigma I equal to 1, 30, each of xi change in x is equal to each x1 change in x plus each x2 change in x plus up to the 30, right? So basically we approximate the area beneath the curve f y equal to f of x, right? Y equal to f of x here, and above the x-axis on AB by using rectangles, as I've already explained here. So let us see the graph below. So when you see this graph, you see this graph, you can see that the change in x here is equal to this b minus a, which is this one, a here, and then the b here. And then we have over what? N, where n equal to the number of approximating rectangles. So for case n equal to 4 or 5, let's say 5, the area beneath the curve will be approximated by that of the 4 shaded region over here, right here. It will be approximated by the 4 shaded region over here. So when approximating with n equal to 5 rectangles, or 4, because here is even 4, so let me use 4 instead. So 4 rectangles, we will have the area under the curve as area equal to f of what? x1 change in x plus f of x2 change in x plus f of x3 change in x plus f of x4 change in x. So that is it. So let's look at the second figure as well. This is the second figure that we have over here. So looking at this figure, we have how many rectangles? 1, 2, 3, 4, 5, 6, 7, 8. Therefore, our n is equal to what? 8 rectangles. So the area beneath this curve, this is the curve, right? So as I didn't tell you here, for this one, this was also the curve, right? This is the curve. So now we have 8 rectangles. So the area beneath the curve will be approximated by that of these 8 rectangles. So in this case, the n equal to 8, we will have an area of a equal to f of x1 change in x plus f of x2 change in x plus up to f of x8 change in x. And therefore the sigma notation or the summation notation is I equal to 1 up to the 8 f of what? x1 or I change in x. So this is something that I need to take note. So in general case, we can say that for n number of rectangles, area is equal to this sigma I equal to 1 up to the number of the rectangles f of what? xi, and then the change in x, where I've already told you that the change in x is equal to the b minus the a all over the n, where always the b minus a, the a and the b are the last ordinate here, the last x values, the first and the last x values. This will be your b and then the a, and then the n will be the number of rectangles. So this is all about Riemann sum, and in my next video we are going to solve some examples.